Okay. So, like I was saying, it's this kind of technique, a lot of money in it. I mean, you don't need, just to be honest, you don't need a major in chemistry to have a really decent job, but you need experience on this sort of thing. And man, they'll take you on. Okay. Concepts and terms of all chromatographic methods. Okay. All chromatographic methods. Separate what from what? What would you say, Miriam? Miriam, what would you say? What's the technical word for the thing that you're after all the time? The thing that you're after, the compound, the chemical, the analyte. All chromatographic methods separate the analyte from the solution, whatever you want to call it. The solution, the lake, the extract, the mixture, the... Have we talked about standard addition technique? We have, right? We have, right? We have talked about standard addition technique. There's a great word to use here then. Separate the analyte from the, there's an M, there's a movie about it, matrix. Right? Doesn't matter how complicated it is, it's matrix. Okay, some more terminology that works for everything. I was not here. Already turned in with less. Okay. Adrian, the blank phase. So this works. We've heard of gas chromatography, liquid chromatography. There's a bunch of different supercritical fluid chromatography. It doesn't matter. As long as it's chromatography, all this stuff works. The blank phase transports the sample through the blank phase. Anybody help them? Not first. There's an M. Mobile phase transports the sample through the stationary phase. All right, so if that's the case, Kathleen, what's the mobile phase in this case? My little demonstration thing. Where's Kathleen? Okay, there she is. What's my mobile phase? It would be the liquid, the water. Stationary phase, everybody, is the filter paper. The paper is the stationary phase. Okay. Elution chromatography, a kind of a special category of chromatography, separating analytes from their matrices. In elution chromatography, well, what is it first? This is supposed to be a general diagram of it. Jeff, what's elution chromatography? How would you describe that, what's going on in that picture in words? What do you have to do to keep it going? Yeah, all chromatography is separation. But elution's kind of special in the sense where you have to keep adding what up on top? Well, the liquid. We're not supposed to say liquid though. We're supposed to say the what phase? The mobile phase. You got to keep adding the mobile phase, which is pretty much true for all chromatography. And your sample elutes to the end. Okay? You can't stop. Because if you stop adding the mobile phase, it's kind of like pulling this guy out of here. Right? It's no longer, I mean, the water might keep going up a little bit, but it's done. It can't. There's no more water. Right? So, he is kind of done already, isn't he? Okay. In elution chromatography, what makes, so in other words, so you drop your sample, your mixture on top, and you just keep adding mobile phase. Okay? And these are, I guess these are columns or something. They're just stuffed, packed columns. They're stuffed with anything. With chromatography, I'm sure there's better things that act as stationary phase than others. But again, we'll leave the rest of the story for when we talk about liquid chromatography. Anyway, this is the general idea. So in elution chromatography, what makes A and B go down the column? Erica, what makes A and B go down the column? Where's Erica? Erica's not here, is she? Kat, what makes A and B go down the column? Yeah, the mobile phase. In this case, you could also say gravity maybe, but gravity's not going to be good enough if you don't have the mobile phase. The gravity's definitely pulling that mobile phase down. It's very different than what we did here with this. This was capillary action. But in both cases, the answer is the mobile phase. It's always mobile phase. Okay. What's in the column? It could be anything. In this, like ground chalk or something. We'll talk about stuff like that when we start talking about liquid chromatography. Okay. What's a chromatogram? Amanda, what's a chromatogram? Yeah, a graph that shows you what's coming out at the end of the column, right? It's a graph that now it's reading some signal. It doesn't really tell you what it is. It's just telling you a signal, right? It's a graph of, yeah, this is a good one to say a detector signal versus, what do you think this is, the x-axis? Time. All it is just a plot of detector signal versus time. Okay. Looking at our little chart here, Pedro, when would you say A and B are starting to separate? At T1? Yeah, I would agree with you until I was looking at this just before class, and I'm thinking, well, T2, yeah, they're separating this whole time. It's really, I used to always answer T1, 2, because you see the two bands starting to separate, because in here they're all mixed up. But from the very beginning, you can't stop separation. So from the very instant beginning, it's separating. I mean, it's separating the whole time, but you can't stop it. You can't stop separation. I mean, it's just going to happen.
So since the beginning to the end?
Yeah, I say in the very beginning, it's starting to separate. You can't see it. It looks like I should reword the question to, at what time can you tell A and B are separating? Then you would say T1. But at what time do they separate? Are they starting to separate? Oh, it's from the very beginning.
Oh, I get what this picture is.
Okay.
I thought it was just a bunch of separate tubes, but it's like showing the tubes.
Oh yeah, sorry. At time T1, at time T2, at time T3, at time T4. Sorry. Yeah, I should have. Yeah. So it's supposed. Sorry, I should explain that. So yeah. Did you get it? Same tube, different times. Okay. And then our little chromatogram is at the end. See, they're the same times. T0, T1, T2, T3, T4. What the detector's seeing. Okay. So at T0 and T1 and T2, the detector's not seeing anything. Okay, there's no detector signal. Pablo, at what time does A come off the column? A comes off at T3. Notice how right off the, off the column. So yeah, it's separated. At T2, it's definitely separated. We could have chopped this dang thing off and put it right up there. Wouldn't have had it waited. So it would have been fine. But you can't see what's going on inside the column. And notice how they read the time that T3, the time that A comes off is at the very center of the peak. And notice how it's getting higher and higher and higher, and then lower and lower and lower. Why? That peak. Is the concentration the same throughout that peak? No, in fact, it must be the most concentrated where? In the middle. Yeah. It's the most concentrated in the middle. Hold this guy on the side, pick him up and hold him on the side, and that's what the concentration would look like in there. All right? It's going to be really concentrated in the middle. Okay? And that's going to cause some problems. We'll talk about that. And B comes off the column at, everybody, T4. Okay. So you could collect that stuff, right? Start collecting right around here for A and collect it in a beaker. Let it drip in there. You'd have pure A. Little beaker, you have pure B. Okay. Oh, I just answered the question. Yeah. So number 8, yes. I'm skipping around here. Which one am I on? I'm on 5. Which compound A or B spends more time in the stationary phase, Anna? They came off at different times. On which compound, A or B, spends more time in the stationary phase? B, yeah, right? Because he took longer to get off of the darn thing. Which compound spends more time in the mobile phase? Adriana, what would you say for that? A? B? Or trick question? Think of it this way, kind of like here too. These molecules, the whole time they're traveling up in this filter paper, there's a dynamic equilibrium going on. Either they're stuck or they're not stuck. Now, when they're not stuck, they're moving up at the capillary action rate, whatever the mobile phase flow rate is, right? When they're not stuck. And then they get stuck again, and they're not moving. Even though the mobile phase keeps going, they're stuck. And they start moving again. And when they move up the mobile phase flow rate. So the point is that all these guys, both A and B, had the same distance to travel. And when they move, they have to move at the same speed. And they can only move when they're in the mobile phase. So what does that mean? They spend the same amount of time in that mobile phase. They have to, because they traveled the same distance. The only way that they can spend different amounts of time in the mobile phase is if somehow you can get them to travel different distances. But you can't. I mean, it's the same column. They both have to travel through from the beginning to the end of that column. And they're only moving when they get unstuck and then the mobile phase. It's kind of a trick question. How about, is there more of A or B? Miranda, do you have any insights into that? Could you say whether there's more of A or more of B? Well, pure A or pure B obtained at the bottom of the column. Would it be more of A? It's a bigger peak. There should be more of it. There's a problem, though. Imagine your little, use this guy. Our little detector, you remember using those little Spec 20s, right? Remember, they read absorbance, okay? And every different color is a different wavelength. So you have to set the Spec 20, though, to some wavelength. It's 512, right? How well does the sample absorb at 512? Well, maybe, I don't know, yellow absorbs great at 512, but red doesn't. But there's a heck of a lot more red, right? So it's the ability for that. It depends on the detector. You can't, just because the signal's bigger doesn't mean you have more of it. There could be a very small amount of A, but he really absorbs really, really well at 512, so the peak is huge. Whereas this guy, B, he doesn't absorb very well at all at that wavelength, or whatever the detector's at. So he needs a whole lot of it just to absorb that much, to give that signal. Make sense? So you can't judge it. You have to make a calibration curve and shoot this stuff. So you can't tell, right? There's not enough information on 7. You have to know, you almost have to shoot a pure and see what that signal is, right? And to see which one there's more of.
So it just tells us what it is, not the amount.
Well, it just tells you that there's something pure at this time.
But we still don't know what it is.
You have no idea what it is.
We don't know the amount of it.
And you don't know the amount of it. But you know that.
Then why do we do this?
Okay, what you could do. Okay, that's for a general problem shooting thing. Let's say you did this, and then you got, okay, this peak. And if you knew which dye it was, I figured out that he is the blue dude on this shelf. I can buy him for $11.99. So I'm going to make up a known concentration of him, and I'm going to put him on this machine, and I get, such a peak area. Well, then I can see this peak area is this amount, my known peak area is this amount. I can figure out what concentration this is, but just by doing a little ratio, right? That this peak area to the unknown has to equal the peak area of the known over its concentration of the known, right? So there's only one unknown in the equation. Just do a little ratio. So you can figure out exact amounts. Okay. And you can also figure out exactly what he is by taking that 11.99 bottle off the shelf, putting it on here. You get the exact same time. Odds are that's it. It's not guaranteed, but man, these retention times are really different for different compounds. So for the same compound, he's always going to have the same retention time, even if he's more dilute. It'll just be a smaller peak is all, but he's always going to come off at that time. Okay. Okay. Are A and B more dilute, Miranda, or concentrated when they come off the column in comparison to when they started up at the top? Or do they not change? Well, they're trying to give you a hint. Notice how it's really dark blue up on top, and it's kind of light blue at the bottom. But
Because they're getting diluted by the mobile.
they're getting diluted by the mobile phase big time. It's a consequence of all chromatography. Mobile phase moves you through the column, but it's also diluting you the whole time. So they're much, much, much more dilute. You can kind of check it out here. I have a really dark line when I started at the bottom. Now look at it. It's getting more and more dilute as it goes up. Okay. Miriam, instead of plotting time on the x-axis, what else could we put? Instead of time, and get the exact same plot, we could put what, maybe? Well, not concentration, not really. Distance traveled could be one, yeah.
Yeah, because they're traveling the same distance.
Well, yeah, that's true. That wouldn't work. Distance won't work. They get a good point. So instead of time, the only really one I can think of is the amount of mobile phase you've added. That's the only other really one I can think of. Yeah, the amount of the mobile phase. You've added 1 mil or 2 mils or 3 mils or 4 mils. You're adding like, I don't know, 10 mils a minute or something. But the amount of mobile phase you've added could be an x-axis. I really can't think of another one. Which compound, A or B, here's a good question, is more soluble in the stationary phase, John? Which compound, A or B, is more soluble in the stationary phase? B. Why? He's right. Why? He said B, and he's right. It spends more time in the stationary phase. It's stuck there much more often than A, right? So you can kind of think of soluble as a much better word to use than stuck, because soluble means, oh, it's dissolving, but then it pops off, and it's dissolving, right? It's going in and out of being dissolved. It's a much better word than saying stuck, but technically it's the same thing.
But it's in there
Right.
because it spends more time in the station. And
Yeah.
It's already decided up there that both of them spend amount that's in the mobile phase. Oh, okay.
Yeah.
Got it.
Okay. So the one that's more soluble in the station, the compound that's the most soluble in the stationary phase is going to come out last, because he loves the stationary phase. Like dissolves like, right? How about which compound, A or B, is more soluble in the mobile phase? Adrian, what would you say for that? Which compound, A or B, is more soluble in the mobile phase? In order for this guy to work, they both had to be soluble in the mobile phase. Everything has to be soluble in the mobile phase. If it's not soluble, it's not going to work. So it really doesn't matter. They just have to be soluble in the mobile phase, even if it's just a little tiny bit. They need to be soluble in the mobile phase. So you can't tell which one is more soluble. You have no clue, because it doesn't interact with the mobile phase. It just dissolves into it and stays there. It's not like the stationary phase where it remains in the column at the same position. Okay. So which compound is more soluble in the mobile phase? You don't know. They're both soluble. That's all you can say. Which compound A or B is strongly retained? So I'm just playing with terminology. Which compound A or B is strongly retained in the stationary phase, Kathleen? Is more strongly. What's that? B, yeah, right? Because B is taking longer. It's more strongly retained. Are compounds A and B, Jeff, of homogeneous concentration throughout their respective purely separated bands? Yeah, you can. A hint is the chromatogram. Homogeneous means same throughout. What is a band? A band is, here's a band, there's a band, here's a band, there's a band. All right. Is it the same concentration throughout? No, it's the most concentrated in the middle. Right? Look at the chromatogram. Right in the very middle. Right when the middle of that band is coming off, the signal's at its highest. So that means it's most concentrated there. Okay. So any questions on that? Did we get them all? How would the chromatogram change? So the chromatogram, let's see it. Oh, it's right there. Here's the chromatogram. How would the chromatogram change if the amounts of A and B were doubled, Cat? Somehow we made that initial concentration twice as high of our sample. What would happen to the chromatogram?
Why would we get the same signal?
It'd be wider at the bottom.
They have a less diluted. Yeah, it'll be less diluted, but still, should we still get off the same signal?
It'll come up.
That would be the same.
They're going to absorb, but will the signal be higher, lower,
Wouldn't it be
wider?
the concentration be a little bit more?
It'll be high. Signals will be higher.
But it's going to be at the same place?
That's what's important. What Kat said is that the signals are going to be higher, but it's at the same time. That is key for chromatography. If that wasn't true, chromatography would literally be worthless. It really would be. So just sketch one. Sketch time versus detector signal. Make sure you center it at the same time, T3 and T4, whatever it was. They should have numbers down there, 10 seconds or whatever. At 10 seconds, compound A always comes off. If there's a little peak, well, there's a little bit of A. Big peak at 10 seconds, there's a lot of A. Okay, so that time is key for chromatography. So you'd have it flat, much fatter peak. And B is a smaller peak, though, right? So I agree with Pedro. It should be wider, but also higher. Right? So you have the same time. What is it? T4 and T3. But like I said, it'd be better if they had actual numbers. 10 and 20 seconds. Time will be the same. Signal is higher. Right?
But only the time at the middle of it.
Yeah.
The highest point will be
Yeah.
in the middle.
So that they always go by the time by pick. That's why they probably take the middle as being the time, is the time you go by, because things are gonna get wider, things are gonna get narrower. So yeah, you always go by the middle. He's the guy who's not gonna change. Right. Good point. Okay. Zone broadening. Okay. Now, things have gotten to the point where we will pay 35, 40 grand for that machine upstairs because it gives really pretty peaks. Nice and sharp peaks. I can put caffeine, I can put Dr. Pepper or whatever on this machine, and I get all these pretty, if I do everything right, get all these pretty peaks. One peak for every single pure compound in that can of Dr. Pepper. So that, what does that mean? That means that, well, the recipe for Coca-Cola, everybody knows it. Right? You just can't reproduce it and sell it. we can go find out what it is right now. So gasoline, anything, you can get nice, sharp, pretty peaks. You pay a lot of money for that. If things get fatter, wider, the peaks start overlapping, it's things, you don't get nice pure separations. You're not going to want to pay for it. So you want as small of zone broadening as you can get. This is a really, really bad thing. This is what causes peaks to be fat, zone broadening. And there's two reasons for it. It's diffusion is what we're talking about. There's two types of diffusion that makes these peaks fat. Here's a picture of one of them. 1, 2, and 3 are just identical molecules. That's all. Okay? And this is the band. It's hitting this band is passing through the stationary phase. Okay? And it's saying that this band is getting what? It's getting wider or narrower as it passes through. It's getting wider. Good thing or bad thing? Bad, right? You want pretty peaks. So why, and according to this picture, why did it get wider? Because here, look at that. Before it hit this little chunk of stuff, man, all these molecules 1, 2, and 3, they're at exactly the same time. They traveled different distances through that column. Can you see that? They took different paths. 3 took the straightest one. 2 took a little bit of curvy. 1 really had to mess around, right? So it's going to take even longer for 1 to get through. 3 got through pretty fast. So they took different distances. They traveled different paths, whatever you want to describe it, but that's called eddy diffusion. That's called eddy diffusion. Now, you said that there's 2 types, though. The other type is, let's say if you take a look at that guy, what he looks like. If I could draw it, now he's really concentrated here, and then he's not so concentrated here, right? Kind of trying to draw lighter. He's the most concentrated in the middle. What happens in nature with things that are really concentrated and that sort of thing? What happens in nature when you have really concentrated stuff, or stuff that's more concentrated than other stuff? What does nature do? Stuff spreads out. In fact, though it spreads, though, from what to what region? High concentration to low concentration. So, and you can't stop it from happening. And we said from the very beginning, look at this guy. We have the center is the most concentrated the whole time, no matter where you're at. Well, that means that stuff is spreading out even more, simply because it's more concentrated in the middle, less concentrated on the sides. And you can't stop it from happening. That diffusion, going from high concentration to low concentration, you just can't stop it from happening. And what's weird about this type of diffusion is it's diffusion that's in the direction of the mobile phase, and also diffusing in the opposite direction of the mobile phase. It goes both ways, because high to low, right? So that diffusion of high concentration to low concentration within the band is called, do you want to get that out of the reading? Longitudinal diffusion. Longitudinal diffusion. Okay. All right. One question, and then we can call it a day. What's an easy way to decrease the effect of each type of diffusion described above? Can you think of something? By making it, oh, that you could, you had all these little particles, the exact same size, right, and packed them all uniformly. That would help the eddy diffusion problem, but wouldn't help this guy's problem, right? You still have that. But you're on the right track here. Does that make sense? So if you make all this nice uniform packing, man, that's really going to help eddy diffusion. It's going to decrease it. But it's not going to decrease the amount of longitudinal diffusion. Well, this longitudinal diffusion, it's just a consequence of being the most concentrated in the middle and less on the sides. So you're starting at some width. You want to end up shorter when you reach the end. You could just do what to the column? Cut it in half. Just use half of it. That's the only thing I can think of that you can to shorten the distance, and it decreases the amount of eddy diffusion because it decreases the time. Not only does it shorten the distance, but it shortens the amount of time for it to do longitudinal diffusion. It does both. Okay. So the distance for the path and also the time. Okay. So what can you expect for a quiz? This is where things are going to be different from the class that you've experienced so far in analytical chemistry. Your quiz, you're going to, when you come in next class period, there'll be a quiz over there. You attach your bold words for the next reading to the back, probably another book of them, right? But the questions are going to be just this stuff. I'm going to take something here, something there, some comment, right? Have you draw a chromatogram? Right from here. So this is what you want to take a look at.
So we don't have homework?
Just
Besides the bold words?
You have the bold words. But take a look at this, though. This is where I'm going to pull the questions from. So have a good day.